So you guys know I've got a degree in biology, so I love it when people ask me questions about biology, and I've taught chemistry a long time. I love those science questions. So my daughter, she asked me a question, which made me all excited. She says, Dad, what did the cell say to his sister when she stepped on his foot? Mitosis. You know, I am so proud of her. That's my girl. That's my girl. All right. All right. It's true story, though. True story. All of it. All of it. So anyways, we're on topic 13 now, and that is going to lead us into a concept called chemical equilibrium. And when we have equilibrium problems, chemical equilibrium, you will notice that you'll see a double arrow like this in the equations. It won't be a single arrow anymore. You're going to see double arrows. So we call this a bidirectional arrow. And let me give an example of that. If we were to take lead ions, aqueous, so we have lead dissolved in water, and we take chloride ions dissolved in water, and they react together, we will form a solid lead chloride. And this is a precipitate. You might remember from lab, we take little drops of different things, and sometimes it got cloudy. That cloudiness was because a precipitate formed. That's a solid that came from two different solutions. That's a precipitate. So this is a reaction that hopefully you can identify with a little bit here. But if we take this now solution that's got lead chloride solid dissolved, or lead chloride in it, if we heat that, the lead chloride, if we heat it, the following reaction happens. So the reverse happens. If we heat this up, the solid lead chloride in the solution will break apart into lead ions and chloride ions. So in other words, this reaction can happen, but the reverse reaction is also possible. Because this reaction can move in both directions, a bidirectional arrow is used to express this. I can't talk today, guys. Sorry. Let's try to get through this anyways. So a bidirectional arrow is used in this process. So we would say that lead chloride, or lead ions and chloride ions, can produce lead chloride, precipitate a solid, and the solid can also break apart into the ions. So let's take a look at an illustration, shall we, of this actual reaction. So let's take a look at this here.
If a solution of lead ions is added to a solution of chloride ions, a precipitate of lead chloride forms. The equation for the reaction looks typical. If the sample is heated, the solid lead chloride goes back into solution. The reverse reaction takes place. This is an example of a reversible reaction. In the equation for such a reversible reaction, we use a bidirectional arrow.
So I really like that video. It illustrates what we're talking about here to remind you of what precipitates look like, and just the kind of visual of everything that we're talking about with this reaction.
Chemical equilibrium.
Now, you might want to pause that and go back and listen to that. Just side story. My students, when I was teaching in Denver at Cherry Creek High School, really bright kids, they took a look at chemical equilibrium, and after explaining to them that reactions can go forward and backwards, they decided to sound out what it would sound like to pronounce chemical equilibrium in reverse. And I thought it was interesting, and they asked if they could record it, and as part of my lesson. So this is what they actually said into the microphone.
My ear bill, I will keep looking back.
I don't know how they did that. So that's what they said, and then when I play it in reverse, we get this.
Chemical equilibrium.
It's just cool. I don't know. Anyways, so what is chemical equilibrium? This is established when the forward reaction proceeds at the same rate as the reverse reaction. So we talked about these reversible reactions, this double arrow. If the forward reaction is occurring at the same rate as the reverse reaction, we're at chemical equilibrium. That means we're not gaining more product or more reactant. I like to use the analogy of like a two-store, maybe shopping center. If the rate of people going down the stairs is equal to the rate of the people going up the stairs, the amount of people on each floor remain constant. So at chemical equilibrium, we have our two floors, and if we think about in terms of a store, you got a population on both. The concentration on them is the same, yet people aren't locked into these spots. They can go up and down the stairs. And overall, the concentration is not really changed on the two as people move up and down the stairs. That's what chemical equilibrium is. So to further explain this, I'm going to use this reaction here. This is iron solution, so it's a solution with iron ions in it, and a solution of thiocyanate ions in it. Both of these solutions are clear. So you take these two solutions and pour them together, and what will happen is the iron will combine with the thiocyanate to make a complex ion, and this is iron thiocyanate complex ion. This complex ion makes a reddish color. It's different than a precipitate. A precipitate is a solid in the solution. It makes it cloudy. This is still an ion, so therefore it doesn't make it cloudy, but this ion reflects red radiation from light, so it will make the solution look like like food coloring in it, I guess. It'll be transparent still because this ion is in here, but it will not be cloudy. Anyways, this reaction does not have 100% product. The reaction never finishes. It changes back and forth at equal rate between the reactant and the product in chemical equilibrium. So this reaction never finishes. The ions here will combine to form this complex ion, and this complex ion will break apart to form this. Just like the shopping analogy I made. If you think about maybe the reactants as the first floor and the products as the second floor, the concentrations of these two are not changing, but they're free to go back and forth. So I've got a few videos that illustrate this quite well. So let's first take a look at what this reaction really looks like.
When a solution of iron 3 nitrate is added to a solution of sodium thiocyanate, the red-orange iron thiocyanate complex ion is formed. Although the reaction looks complete, substantial amounts of iron ion and thiocyanate ion remain unreacted in solution.
So what's important to grasp here is this looks like the reaction's over, and I think it's really cool watching two clear solutions go together and it makes a red solution. It looks like it's complete. It's not changing color anymore, but what's actually happening here is the iron thiocyanate is breaking apart into the iron and thiocyanate ions, which are clear, but also iron and thiocyanate ions are coming together to make this iron thiocyanate. So an animation of this that kind of illustrates what's going on is the next thing I'm going to show you.
When iron 3 ions contact thiocyanate ions in solution, they can react to form a complex ion, iron thiocyanate. As the reaction proceeds, product molecules can react in the reverse direction to separate and reform the original ions. Eventually, the concentrations of products and reactants become constant. At this point, the rates of the forward and reverse reactions are equal, and the system is in a state of dynamic equilibrium.
So if the iron is connected with water, this would be a clear solution, but when we see it connected with the thiocyanate, this would be a red solution. So it's going back and forth and back and forth. Now, the next thing I want to talk to you about is the proof behind this. Like, it looks like nothing's happening. It's got the same color, it's not getting darker, it's not getting brighter. How do we know that this is actually happening? How do we know that we just don't have this locked up, and how do we know this is actually breaking off? And that's what the next video is going to talk about. Before we go into the next video, I want to remind you about something we learned in the first quarter, and that is what a isotope is. What is an isotope? An isotope is an element, and elements have the same amount of protons that has a different amount of neutrons. Sometimes isotopes are unstable, and you can easily identify those isotopes in a collection of atoms. You can identify those isotopes because they're unstable. So we use kind of unstable isotopes to label, to follow what's going on here. So in the next video, we're going to see labeled thiocyanate, and they're going to be labeling a carbon in here so we can keep track of it. So see if you can follow along with this video, see if you can understand what's happening here.
If we produce iron thiocyanate complex using a thiocyanate ion specially labeled with the carbon-13 isotope, and then mix the complex with a solution of unlabeled thiocyanate ion, we soon find that the final product solution contains both labeled and unlabeled iron thiocyanate complex. This means that the product dissociates and then reforms. It demonstrates that the reaction does indeed continually occur in both directions.
So I just want to reiterate what's going on here. In the beginning of this reaction and the experiment, they add iron ions and thiocyanate ions that are labeled. And if there wasn't a dynamic equilibrium, if it just bonds and it just stays bonded, we would see that this right here, this iron thiocyanate, would connect and it would never break. And all the ions would be accounted for by connected with label iron thiocyanates. But what happens in this reaction, what they decide to do here, is they introduce, remember it's just iron thiocyanate here, and if you think that it wasn't going to break off, then it would stay on here. So then they add more thiocyanate ions, and then they find in time that the iron is connected to both iron thiocyanate unlabeled and, do they have one in here? They didn't even do it again. But it would have unlabeled ones, and it would also have labeled ones like this. So you'd have both, a collection of both, and that's the evidence behind that these reactions are never ending, that they're going back and forth, because if it did end, there would be no opportunity for the thiocyanate to connect to the iron because it would all be used up. So our equilibrium constant is represented with a K, and so this is the constant for equilibrium, and this subscript we'll get into in another lesson, but just in general I'm just going to say this is the K for equilibrium. We'll talk about certain systems in a later lesson. So what the constant is, it's a ratio of the product's concentrations to the reactant's concentrations at equilibrium, with each concentration raised to the power to the number of moles that of a substance in a balanced equation. I know this is kind of wordy, so let's just talk about it in symbols.
Nerd alert!
That's Austin Powers, by the way. If you don't never seen Austin Powers, you got to do so. It's awesome. Anyways, so if we take a hypothetical equation here, A plus B yields C and D, the capital letters are representing elements and compounds, and the lowercase letters are representing the coefficients in a balanced equation. So like you might have 2 A's plus a B makes 3 C's, you know, whatever that is. So the little one is the coefficient, the big one is the actual element or ion or compound, whatever. So what the equilibrium expression is, it's the ratio of products, concentration, remember these brackets represent concentration, so we're talking about molarity, to the reactant concentrations. So notice that the products are on the numerator, and the reactants are going to be our denominator. So we're going to say our concentration of C times our concentration of D, raised to the power, if there's any numbers here, we're going to raise them to those powers, divided by the concentration of A raised to the A power and the concentration of B raised to the B power. This is the setup for determining the equilibrium constant. Let's do this. Let's expand on this a little bit and see if we can understand what's going on here. So in this equilibrium constant, if you have an equilibrium constant for a reaction where the K is a very large number, what does that mean? If K is a large number, that would mean you'd have a greater numerator than denominator. And if you've got a greater numerator than denominator, then that would mean you have more product than reactant at equilibrium. So this would be a situation that you are product favored. The reverse is also true. So if K is a very small number, if it's a very small number, that would mean you have a large denominator. So it's you'd have a small number up here. I'm sorry, you have a small number up here and a large denominator, making it a fraction, which would be a very small number. So if K is very small, that would indicate that this is reactant favored. And what I mean by this is, remember I talked about the analogy with the store. With the different levels and going back and forth at chemical equilibrium. Just because you can go back and forth at equilibrium doesn't mean both floors have the same amount of people. There might be a lot more to do on, say, the first floor than on the second floor. So there's a lot more, the concentration on the first floor is a lot greater than that on the second floor, but they're still able to move back and forth. So it doesn't mean that when a reaction is equilibrium, you have half of this and half of this. The K value tells you the relationship between the reactants and the products. And so that's important to note.
Sample problem.
So in this question here, let's just do practice with adding this together. So write the equilibrium constant expression for the reaction in which ammonia gas is produced from hydrogen and nitrogen. So nitrogen and hydrogen react together to make ammonia. So to do this, let's go back to our notes on what we just talked about, that we have for a hypothetical reaction. We set it up like this. So as we set this up with our actual reaction here, we note that we're going to put the products, remember the products here are going to be the numerator. So my product is ammonia, that's going to be my numerator, and our reactants are going to be the denominator. And in this case, I only have one product. In this one here, I had two. Doesn't matter how many reactants or products you have. So my products are on top and my reactants are on the bottom. Now the next thing I have to do is raise these to the power of the coefficient. So ammonia has a coefficient of 2, so therefore it's going to be squared. Nitrogen has a coefficient of 1, there's nothing here, so that's raised to a power of 1, so you don't have to put anything here as well. Hydrogen has a coefficient of 3, therefore hydrogen is going to have a coefficient of 3. So it would be the concentration of ammonia squared divided by the concentration of nitrogen times the concentration of hydrogen cubed. That's how you would write the equilibrium expression for this. I've got 2 workshops in this lesson. So we're going to pause the video here. I'd like you to try to solve these and then start the video again. So, and then we're going to do another lesson. So we're not done yet. A very small little twist I'm going to add to this, and that'll be workshop B. So first try this one right here, pause the video, and give this your best shot. And hopefully you did. So let's take a look if you got the same answers I got. So let's take a look at this. Oops. So for number 1, you should have written the product on top, which was nitrogen dioxide. And there was 2 of them over, by the way, this is your K. EQ. You should have written this on top, and then you'd write your nitrogen dinitrogen tetraoxide on the bottom. There was no coefficient for that, so you just leave it like this. I would normally probably put it the other way around. That's okay. Number 2, I'll do it this way. K equation or equilibrium equals. On top, we've got methane and oxygen, so I'm going to say the concentration of CH4 times the concentration of H2O over, this is important to be able to do, guys, because every equilibrium expression has a different expression, and you have to be able to write it based off of looking at these equations. And the bottom one would be carbon monoxide times hydrogen, but that hydrogen is cubed from that equation. And then number 3, and notice it doesn't take a whole lot of time to do this. You shouldn't be bogged down on this because you'll have to be able to do this to solve other questions. So number 3, we have the concentration of hydrogen squared times the concentration of oxygen divided by the concentration of water squared. So these would be your answers to 1, 2, 3. Now, let's add a little bit more information to this. So in terms of thermodynamics, let's take a look at this equation here. In thermodynamics was the last lesson we did in my class. If you need review on that, you might want to go take a look at that. But anyways, if you take a look at thermodynamics, I've got hydrogen and oxygen reacting to produce water and energy. And this is a reversible reaction in that we can add energy to water and split it. This is called electrolysis to make hydrogen and oxygen elements. So if in this reaction here, if this is an exothermic reaction, it's exothermic because energy is a product. It's releasing heat when we burn hydrogen. We did this in lab when we caught the hydrogen off of when magnesium reacted with the acid and it released the hydrogen. We turned our graduate cylinder over and we lit a match and popped. That's this reaction here. So that's an exothermic reaction. It was a combustion reaction. So if the the change in enthalpy is negative or exothermic, then the reverse reaction would be positive. So since this is exothermic, then the reverse reaction is endothermic, because the reverse reaction is energy and water makes these two, so this energy is required. So if we reverse the reaction, it changes the sign of enthalpy. This is also true with entropy. If we notice here, we've got 2 plus 1, we've got 3 moles of gas becoming 2 moles of gas. So we have 3 moles of gas becoming 2 moles of gas. So it's lunchtime. If the change in entropy is negative, so it's less entropy as we go here, then the reverse reaction would be positive. It's got more entropy. So going from 2 to 3 is more disordered. So as we reverse the direction, we reverse the signs of these things. Finally, if a reaction is spontaneous in one direction, delta G, then the reverse reaction would be non-spontaneous. So whenever you look at thermodynamics, it's the opposite when you talk about the reversible reaction. All right, so if we're going to look at catalysts here and how they affect equilibrium. And some people mistakenly think that, remember we talked about this in kinetics, that if you add a catalyst, you will maybe shift the equilibrium, produce more product than, you know, if you added a catalyst or something like that. But that's not true, because when you add a catalyst, you're not only making it easier to make your product, but you're also making it easier for a product to become reactant. So when you add a catalyst, that lowers the activation energy. So it makes it easier to become products, but it also makes it easier for products to become reactants. So a catalyst speeds up both the forward and reverse reactions. Thus, it does not affect the equilibrium position. The K value does not change when you add a catalyst. So important thing to note. Okay, so next thing I'm going to talk about is heterogeneous equilibria. In this example here, I've got a flask that's sealed, and I've got ethanol liquid in there, and I've got ethanol gas. So there's an equilibrium here where the ethanol liquid will become ethanol gas, and the ethanol gas will become ethanol liquid. So the products will break down and go back into the reactants. So we have this equal transfer here, and we have a constant pressure of ethanol gas in the container. So from what we just talked about, the equilibrium constant would be expressed like this. It would be the products, which would be ethanol gas as the numerator, and the reactants, which is ethanol liquid, as the denominator. So I would represent the equilibrium constant like this. But I want you to kind of take a note here. Because liquid ethanol is a pure substance, its concentration is constant at a given temperature. Its density does not change. In other words, it doesn't make a difference if I've just got a little bit of ethanol here. The pressure here is going to be the same if there was a little bit of ethanol here, or let's pretend this container was much deeper and there was a lot more ethanol underneath. It wouldn't change the vapor pressure. It doesn't matter how much ethanol I have, and in fact, ethanol doesn't have a concentration. It's a pure substance. It's not ethanol AQ, meaning ethanol dissolved in water. This is pure ethanol, and the fact that there is some will create this vapor pressure. So, because this is a pure substance, because it doesn't have a concentration, liquids and solids remain constant and are not expressed in equilibriums. So if you have a liquid, it's a pure substance. If you have a solid, that's a pure substance. They're always constant. You don't change the concentration of liquids and solids, and therefore they're not expressed in equilibrium in the equilibrium expressions. Gases do have a concentration. You can pack more gases tightly together. You can put them under pressure. And aqueous has concentration because you can put more things dissolved in water. But liquids and solids do not have a concentration. They're pure substances. So we don't add pure substances to equilibrium expressions. So having said that, this initial idea we had here is not actually correct, because this is a pure substance. It doesn't have a concentration. Remember, that's what those brackets mean. It doesn't have a concentration. So simply stated, the equilibrium expression for this equation here would exclude the liquid. So it would be simply written as the equilibrium expression for this reaction is just the ethanol gas, just the concentration of ethanol gas. As long as there's some liquid, you're going to get a specific concentration of the ethanol gas. So do not include liquids or solids in equilibrium expressions. All right, this is the final workshop, believe it or not. So there was one before. If you just came to the video here, go back. There is a workshop 1. This is 1B. There was a 1A. Pause the video here and try to work these guys out. And hopefully you did that, and I will go over the answers with you right now. Let's do the answers. So in the first one here, we have a solid hydrocarbon becoming a gas hydrocarbon. And remember, we don't include solids in our expression, so it's just products. So the K value is just the product concentration of C10H8, just this concentration, and this is not included. So this would be the answer to number 1, C10H8. It's kind of funky drawing here. So we wouldn't include that solid. For number 2, again, we wouldn't include the solids. So it would only be this gas, and gas is a product in this one. So this carbon dioxide, it's just the concentration of carbon dioxide. That's all we'd have to do for number 2. Number 3, this is water liquid becoming water gas. Liquid is a pure substance. We're not going to include that. So the expression for this one would just be the concentration of water gas. You could put a G there if you want. Okay, let's look at number 4. Number 4, I've got solid carbon and water gas reacting to make carbon dioxide gas and hydrogen gas. So remember, that's a solid, so I'm not going to include this one. So these are my products going to be on the top. So K equals the concentration of CO2 times the concentration of H2 raised to the power of 2. This coefficient, I'm going to raise it to that power. And then it's going to be divided by the concentration of water gas. And there's 2 of them, so it's going to be to that power. So that would be the equilibrium expression for number 4. And finally, number 5, we have solid iron 2 oxide, and we've got a solid iron. So the equilibrium expression for this one is the concentration of CO2 over the concentration of carbon monoxide. And that's the answers. Let me know if you got any questions, you're confused about anything. I'd be happy to help, and I'll talk to you soon.